Hi guys, today we're going to talk about how Adobe uses Spark structured streaming at scale. I'm Yashin Vijaykumar. I'm a senior engineering manager and architect at Adobe, then specifically with the Adobe Experience Platform and Insight at the Unified Profile team. We're extremely high users of Spark, and we are hiring for people who are experienced with Spark. So yeah, hit me up if you're interested. And now getting into the agenda for today, we are kind of go over multiple high-level topics. Uh, we'll begin with what does lag mean in our structured streaming world. We'll also go about optimizing our upstream processes and how to write some efficient logic on top of it. And lastly, we'll also go over streaming statistics to understand some niches about that. So before we jump anywhere into what we say the tips and tricks, right? We need to understand the ecosystem that we're dealing with here. Uh, so we have a lot of internal solutions. Example, Adobe Campaign, which is an email campaign orchestrator, and Adobe Analytics, which is one of the world's largest vendors for analytics software. So you have a fire hose of marketing information flowing into our system. This data can be coming in the form of JSON, Parquet, or Protobuf, or anything that you can think of. All of this is converted into our own JSON schema, which is a marketing standardized experience data model. We call it XDM. This in turn is ingested into what we call the unified profile, which gives you a 360-degree view for a customer. The main advantage of this is you can do a lot of complex targeting and activation queries like, hey, give me everybody who did a trial of Illustrator in the last 10 days and have added Photoshop to the cart and but have not made any purchases yet. So you can do a lot of complex actions and queries using the unified profile on top of your marketing data. What happens after this is any mutations that happen to the unified profile, they get fed into the fire hose, that is the change feed, a Kafka topic, to keep track of the logical changes made to the entities. And then this is consumed by various downstream applications like statistic generation, etc. Again, Spark all the way. And Kafka providing the transport layer. With respect to structured streaming, we need to first understand the lag. With the streaming mechanism, it's always difficult, right? What or how are we going to measure? So Spark thankfully gives you a very nice streaming query listener, which we can implement on top of to provide our own monitoring. So the thing that we're going to focus today is the on-query progress method. This basically gets invoked as soon as MicroBatch query is successfully executed. So you can see that we have a lot of handles like progress dot number of input rows that got taken in by the MicroBatch. We also had other metrics like process rows per second, input rows per second, input rate, etc. So this is extremely useful to get a programmatic handle on what Spark, as in what the MicroBatch actually sees or saw. Now we take these metrics and we publish it to our own internal metrics system. You can use Prometheus, Grafana, any of the things that you have custom built in your ecosystem. So this way, what happens is as the query is processing, you kind of know what kind of progress has been made. Okay, how much work did we do? But this is not actually enough, right? Remember, we are reading off of a Kafka queue, right? So when you're reading off any queue, you need to understand how much progress have you made relative to the load currently in the queue, because that tells you how much more work has to be done, right? So what we do for that is, so this method we've kind of taken from this excellent blog that I have linked below. So what they do is you get to specify a dummy, you create a dummy Kafka consumer group. And then you create a new instance of your streaming query listener, which takes in this dummy consumer Kafka group. And then what we do is the query progress also tells you what offsets have been read so far, right? Like similar to input rate and all that stuff that we were seeing earlier. We also get an idea of what offsets have we read so far. Now, these can be committed back into the consumer group. So the consumer group is now responsible to the dummy consumer group that we we created is responsible to keep track of the data that we have read so far. Now, how does this help, right? So what happens here is now we can use Burrow, which is like a monitoring companion from Kafka itself, to keep track of the lag. So you will be able to figure out the lag per topic. Now that dummy consumer group that we created, since we are tracking the lag per topic, we commit the offsets also per topic. So we will be able to figure out just from looking at the lag of that consumer group from Burrow, how much work do we need to do more to keep up with the load on the queue? So this is an example of just a random snapshot of our load. You can kind of see like we're going at a pretty high throughput, and this is provided by both the streaming query listener implementations that we have registered with the Spark context. The next important thing is, I would say, like we need to optimize the ingestion part. What do I mean by that, right? So the Kafka, the queue is the upstream process, right? A generic flow would be something like this. You have a topic, you have multiple partitions, and then now this is being consumed by your Spark structure streaming app. The data gets sent from the the driver tells the executors what partitions to consume off of from. Executors read the data from the partitions. The business logic gets executed on the executors, and then it gets written to a sink, or probably some other side effect takes place from the executors. Now, it's quite important for us to optimize this part before we step into optimizing the executor logic as such, because attach a JProfiler, try to optimize the logic. That happens quite often. But then architecturally speaking, there are some settings and configurations that you could do to optimize your upstream load. So here we have like an example, a read stream from the Kafka topic. You can see the format of Kafka indicating how Spark should actually figure out what to read and where to read from. We specify a lot of things like, the bootstrap server, subscribe, the topics to subscribe from, etc., as part of the normal configuration. But before we optimize anything, right, we need to lay some ground rules. We need to keep the executor resources constant, because if you keep changing your executor resources, right, or keep changing your type of executor resources, like CPU type, amount of disk that is there, it's not easy for us to have like a solid experiment. So keeping that in constant, the first parameter that we want to change is the max offsets per trigger. For those of you familiar with structured streaming, it deals with creating a lot of microbatches at scheduled intervals of time. So your trigger interval, if you have a trigger interval of say 30 seconds, it means that every 30 seconds, you're going to trigger off a microbatch to pull data from Kafka. So now, in order to avoid, overwhelming the system, we always should specify how much we should specify how many offsets do we want to pull from Kafka in order to make progress on our system. So this is actually controlled by the max offsets per trigger. So every, say, if trigger interval 30 seconds, every 30 seconds, Kafka goes and pulls, say, 10,000 offsets across all the topics that we have specified from different partitions, and distributes that to the executors. Now, this is extremely important because this decides what QPS you will finally end up with, right? So if you want to go 1,000 records per second, in that case, if you have a 30 second trigger interval, you need to pull at least 30,000 offsets per trigger. So this is something to be extremely conscious of. The next important thing is you want to make sure that your processing time is less than equal to your trigger interval. What do I mean by that? So a lot of the times when we start designing the system or like implementing it, right? They're like, hey, I want to do 100K RPS. Yeah, it's completely fine to have it in our head. But the problem is I can specify, 30,000 QPS or 300,000 offsets per trigger. But then once we start processing, it might not, the resources at hand might not be enough to actually process that QPS, right? So we need to keep an eye on, so the processing time, if trigger interval is 30 seconds and processing time is 45 seconds on average, in that case, you're never going to make up that 15-second gap, right? You're always going to be running behind and you're never going to catch up. So the only way to, if you figure out, oh, how much more headroom we have, is to make sure that first pick an offsets per trigger much smaller and make sure that your processing time is way lesser than the trigger interval, and then kind of do like an exponential approach to keep increasing so that you figure out what is your sweet spot. The next and most important parameter after you've done the first two things that I talked about is the minPartitions. This is not as well publicized as the other two, but what the minPartitions does is it enables a fan-out processing pattern. So it maps one Kafka partition to multiple subpartitions. A lot of the time what happens is, and I did the mistake myself, is I was like, hey, I think I'm blocked on throughput from Kafka because I have only, say, 5 partitions from Kafka. I was like, okay, let's go raise a request to increase the number of partitions from Kafka. And then the pipeline team told me, hey, you know what? You probably don't need that. Why don't you do a bit more fan out? You're probably not blocked by the throughput from Kafka. So and then we explored this parameter. So this way, what happens is every single partition, because it is getting mapped to multiple subpartitions, you are able to pull in way more data and then distribute it across to the executors that you already have and provision. So for a visual effect, we will go to the next slide. But the key idea is you have to rinse and repeat these steps to be able to figure out what is your actual throughput per core. Once you have decided that, you basically know what your application is capable of, and you can figure out your scaling bounds. So for the minPartitions visualization, right? So we have a Kafka topic with, say, 2 partitions. Now we have 3 executors. Now, if I say my minPartitions is equal to 6, in that case, what's going to happen is you can see executor 1 and 2 have partitions 1.1, 1.2, and 1.3. So we have subpartitioned it, and we have allocated across 2 executors. Similarly, 2 has been split across executor 2 and executor 3. So this way, your executor cores are getting proper utilization, and your throughput is not limited by the number of partitions that are there on the Kafka side. What we have noticed in practice is reading, as in doing the scan from the partitions from Kafka is extremely efficient. So very rarely are you going to hit those bounds. So as long as you have a good amount of topics to parallelize across, you should not have to, keep on increasing the partition count on the Kafka side. Increasing the partition count on the Kafka side does have some other negative side effects, but I don't think we want to go in deeper into that rabbit hole right now. Now, so far we spoke about, optimizing the upstream logic, right? But what about the logic itself, the business logic on the executor side? We need to optimize that too, right? As in, there is no magic bullet over here. Usually when we are expressing the logic, it broadly falls into 2 categories. Are we doing it row by row, or are we batching it up? So that is why I've split this into 2 parts here. Whether are we going to follow the map and ForEach paradigm, where we are processing row by row, or are we going to do the map partition in for each batch paradigm, where we are processing a bunch of rows? So for the map example, right, you can see like we are applying a filter on some data set where the signal value is greater than 10. And then we are just mapping the device data, the device field out. So the pros for this approach is that it's extremely easy to code. The cons for this, as in, because this is the first thing that comes into mind, right? Like when we're looking at a data frame, we are kind of visualizing, okay, what happens to every row across every transformation that's going on. The cons is this is slow in most of the cases that are, at least that we have encountered. So there is no local aggregation out of the box for this. You need to specify an explicit combiner. A combiner in Spark is one of the things that I don't like too much about it. Extremely cumbersome to write as an interface. And we have way too many individual tasks that are created in order to maintain the performance for the row by row the row by row processing of performance. The other main thing is, specifically if you're going to write to an external sink or communicate with an external sink, it's very hard to get the connection management right. So given this, let's compare it with the map partition and for each batch approach. Right. So the pros of this is we get explicit connection management, because we're doing batch by batch, right? So for every group of records, we can manage the connection. So the batching and the reuse of connections is well established here. We can do local aggregations using hash maps at the partition level, or any other aggregating mechanism that you can do, right? You can also use the data frame itself, the MicroBatch data frame itself as an aggregation step. So you can, you have a much finer control at that point. The cons for this is you need way more memory upfront, and you can't just say like, hey, I've converted my map logic to map partition and it's just going to work right? You need to tune a bit. So otherwise you're going to end up with out of memory use cases, out of memory cases. It's also pretty ugly to visualize because the map filter and that paradigm is extremely well established. Batch wise, you need to apply a bit more and see it from a different angle. The other thing is, it kind of relates to the first con. You might need a bit more extra CPU per task. This is more like a side effect, right? So if you are, by default, you spark the task of CPUs is set to 1. Now that you're doing batching on the executor side, you might need to set it to a higher CPU count for parallelism. As in the explicit parallelism, the implicit parallelism that you got with map and for each by the huge number of tasks that got created. Now you are responsible for maintaining those tasks within the map partition and for each batch. So it's not like it just disappeared, but you need to now keep that in mind before trying to juice this approach for more performance. So an example of the map partitions or the for each batch thing, right? So in this example, what we're trying to do is we are trying to create some Bloom filters on the executor for every microbatch, and we're going to send them to Redis. So you can see that after the microbatch is defined in batch df, we are setting up a Redis connection in the for each batch in the start. And once we have set that up, we are doing some local aggregation using the microbatch itself. So we're doing a dot distinct that collect on the microbatch itself. So again, this is a local aggregation that we're talking about. And then we use the Redis connection that we created at the top of the partition to send the data to the external sink that is Redis in this use case. And once we are done, we close the Redis connection and we are done. So this way, we saw an example of all the things that we spoke about in the pros and cons. The next super important thing that actually helped us is speculative execution. Speculative execution in Spark. This should not be a huge surprise to anyone who's come from, the Hadoop MapReduce thing. Speculative tasks basically get created when a particular stage is slow, like when some tasks are slow. once we reach its threshold, a speculative execution is set to true, duplicate tasks are launched, and we basically have a race to say like which task ends first, we'll take the results from that task. So extremely useful when your tasks, the tasks and the side effects from the task are idempotent. And in some of our cases, this was pretty useful. Where this becomes extremely useful is trying to maintain your average and median times, because failures are a common part of cloud, or whether you're doing it in your own data center. Some VMs might become very slow, some networking issues might happen. So specifically for long running things, right, you can think of it like as a parallel with a high throughput API, with hundreds of instances. Obviously, one or two are going to go crappy and they're going to disappear. So it's always good to have the speculative execution on if the conditions work for you. And what you will see is one important parameter is the speculation quantile. Now, this tells you what fraction of tasks must be completed before speculation is enabled. So 0.9 means at least 90% of the tasks for a given stage have to be completed before speculative execution can be triggered. So we can see here that 10 tasks were probably spun up and then they got killed because the other ones ended. But the main takeaway is we're trying to make sure that the time is not going multiple standard deviations away from the average time taken by the tasks. Now, a very common thing, one of the most powerful things that we get with Spark structured streaming, right, is that the streaming statistics. So let's look at some pitfalls during the aggregate step that we have. Let's take a very simple example. This looks familiar to you. This is an events data frame that we have created from the read stream. So we're reading from Kafka for some retail company, and the events have purchases, add to carts, clicks, views, etc. So let's take two different scenarios, right? Two different structured streaming queries. So one is event count by hour. So we want to get all the event types that have occurred in a sliding window of one hour. And we also want, sorry, not a sliding window, in a window of one hour. And we also want to get the product count by hour. What products have been sold in this past hour? So we make a filter on the purchase events, and then we are going to group by the product ID. So they look very similar to each other, right? But then how does the results in the state store look? Because Spark has to maintain those results somewhere, right? So it will look something like the key would be, from 8 p.m. to 9 p.m. for purchase events, you have 500 events that came into picture. Similarly, for add to cart, you have 555K. So this is how the results table would roughly look like. Now, how would the results table look for the second one, right? Pretty similar, but you can notice that it's like product one, product two, and then product XXXXX. So, and then add to the fact that this is on a hourly basis, the cross product is going to be pretty high. So for the first one, it's of lower cardinality. We are all good to go. We don't have any big issues over here. For the second one, like I said, product IDs could be in, say, hundreds of thousands. And then since we're doing a cross product on the hour, 24 hours in a day, so it could get really nasty and can be a very high cardinality over here. So the state store issues mainly come from the fact that by default, they're stored in memory. That is, they're managed by the JVM. Because the HDFS state store, this is one of the biggest issues with them. A large number of keys in the state store, obviously, is going to cause now a GC pause. So more GC pauses means higher latencies and increased lag on your streaming components. So what we want to do is we want to switch to an off-heap state store, right? So one example that we have over here is in the proprietary version of Databricks, you get the RocksDB state store provider. So in this way, you can safely manage way more keys, like 100 times more in the state store safely, rather than having to have failures or GC pauses. You take a slight hit in with respect to the the write and reads, but it's not exactly a big problem over there. You can also implement your own persistent off-heap state store provider. There are a lot that are available right now for RocksDB. One example is you can use Redis 2. One thing to keep in mind is you want to think about what your output mode is, whether you're doing a complete output or append output. So that's something, or an update. So that will also decide how efficient your state store choice is going to be. Another thing that I quickly want to touch is skew. Some partitions might be extremely skewed when you're getting data in. So what will, and this is very real, right? You can't always control what data you're getting. So in that case, you will, when you're processing these partitions, you can have out of memory issues or connection failures. So even if say 99 out of 100 tasks pass, if that one task fails, your stage is not going to move past, and you're going to be stuck in that loop. So one thing that we can do to help out is repartitioning. So just repartition by whatever column you think might help you. This will be one easy way to get out. But repartitioning might not be enough all the time, right? So we want to add some salting to the logic. So everybody has a unique way of trying to add some salting logic to the columns. One simple way is you can always have like a target partition count in mind, and then you can just randomize your salt key so that you have a much more uniform distribution, so that you can split the data uniformly across the various partitions, rather than some other column which has a much more skewed distribution. So one thing that I wanted to go into was about the target partition count. But then I will leave this for the slide. One thing that I'll say is, if you are trying to create a target partition count, you might want to keep in mind to try to mimic the HDFS block size, because that will help you in the reading of the final block that you have written, in case your final sync is the HDFS. So one last tip which I want to focus on is, if you're using, say, Redis as your sink, right? Or you're probably using some other HTTP sink also, you might want to look into pipelining, whether it's on the HTTP side or on the Redis service side. So without pipelining, every time a client sends a request, it gets an ACK back, and only then it sends the next request in. With pipelining, you send a bunch of requests, the server does the batching on its side, and then sends requests back all together. So one example that we have in the forEach batch example that we saw is, what you can do, get the Redis connection on the per partition level. You set the auto flush to false, so that it tells the client, hey, don't send the request unless I explicitly ask you to. You group it locally in your forEach batch, so according to a group size. And then you keep adding things as if it's business as usual, as in doing operations on that. And then you do an explicit flush. So that tells Redis or whatever client you're using, I need to actually send the commands in now. And then you wait for the thing and you get the results back. So we're almost out of time. So I think that's all that I had for today. Please do leave feedback and let us know how we can improve our stuff, if this was useful to you. And that's all. Thank you.